Video script, 10 chapters. Chapter 1. Images of McDonald's ice cream cones, industrial factories, machines producing cones, manufacturing process. Upbeat industrial music. You've probably eaten a McDonald's ice cream cone. That iconic dessert of creamy soft served inside a crispy cone that costs just $1 or $2. But do you have any idea how that cone is actually made? We're not talking about the ice cream. We're talking specifically about the cone itself. That perfect, uniform, crispy wafer that seems simple, but hides a fascinating industrial process. The McDonald's cone isn't an accident. It's the result of decades of food engineering, process optimization, and obsessive quality control. Every cone you hold in your hand went through a journey involving specific ingredients, specialized machinery, exact temperatures, and rigorous inspections. And all of this happens at massive scale. McDonald's serves millions of cones daily around the world. To maintain absolute consistency, uniform quality, and low costs at such enormous volume, the process needs to be extremely sophisticated. We're going to reveal every stage, from ingredient selection to the moment the cone reaches your hand. Prepare to never look at an ice cream cone the same way again, because once you see how industrial food is really made, your perception changes completely. It can be fascinating. It can be disturbing. Usually it's both. We start with the basic ingredients. The cone is essentially a conical wafer, a type of extremely thin and crispy cookie. The main ingredients are wheat flour, sugar, vegetable fat, eggs, and soy lecithin as an emulsifier. Simple, right? But the exact proportions and quality of each ingredient are crucial. The flour needs specific protein content to create the right texture. Sugar needs particular grain size to dissolve uniformly. Vegetable fat needs exact melting point. Small variations create cones that are too soft, too hard, irregular, or that break easily. Chapter 2. The process begins in specialized factories that produce exclusively wafer cones. McDonald's doesn't make its own cones. It outsources to specialized manufacturers like Joy Cone Company in the United States, which is one of the world's largest ice cream cone producers. These factories are massive industrial operations running 24 hours a day. The first step is preparing the batter. Ingredients are mixed in giant industrial mixers that can process tons of batter per hour. Consistency is crucial. The batter needs to be liquid enough to spread uniformly, but not so liquid that it won't hold shape. Viscosity is measured precisely and adjusted continuously. Batter temperature is also controlled. Too cold and it doesn't flow properly. Too hot and it can start cooking prematurely. Refrigeration and heating systems maintain ideal temperature. Once prepared, batter goes to wafer machines. These are similar to waffle makers, but specialized for cones. They consist of heated metal plates with conical molds. The process is continuous and fast. Batter is poured onto lower plate. Upper plate descends, pressing batter into thin, uniform layer. Plates are heated to approximately 200 degrees Celsius. Under heat and pressure, batter cooks in seconds. Water evaporates, sugar caramelizes slightly. Proteins and starches form crispy structures. Timing is critical. Too little time and wafer stays soft. Too much time and it burns. Sensors constantly monitor temperature and timing, adjusting automatically. When wafer is ready, plates open. The flat, hot wafer is quickly removed by robotic arms. Here comes the crucial part, molding. The wafer is hot and flexible. It needs to be rolled into conical shape before it cools and hardens. Chapter 3. Molding happens in a fraction of a second. The flat wafer is placed on metal conical mold. Another mold presses from outside, forming perfect cones. Pressure needs to be exact. Too much pressure and wafer breaks. Too little pressure and cone doesn't hold shape. The process is so fast it happens while wafer is still hot and pliable. Seconds later, wafer cools and hardens in conical form. Molds open and cone is ejected. Cones then pass on conveyor belt through cooling tunnels. Cold air circulates, lowering temperature rapidly and uniformly. Controlled cooling is important to prevent cracks. If cone cools too fast, thermal stresses cause fractures. Too slow and production slows down. After cooling, cones pass through first inspection. High-speed cameras photograph each cone. Computer vision software analyzes shape, color, structural integrity. Cones with defects are automatically rejected and removed from line. Common defects include cracks, burns, irregular shape, holes. Rejection rate is constantly monitored. If it increases, indicates process problem that needs correction. Approved cones continue on production line. Next step is applying internal coating. You notice the inside of the cone has a slightly sweet layer that helps waterproof it. This coating serves multiple functions. First, it adds sweet flavor. Second, and more importantly, it creates barrier preventing ice cream from softening the wafer. Without coating, melting ice cream would soak cone quickly, making it soft and unpleasant. Coating is typically made of sugar, vegetable oil, and lecithin, applied as fine spray inside the still warm cone. It adheres to surface and solidifies, creating thin but effective layer. Chapter 4. Coating application is delicate process. Cones pass through chamber where spray nozzles pulverize coating uniformly inside. Amount needs to be exact. Too little, and it doesn't waterproof adequately. Too much, and it alters flavor or creates too thick layer. Sensors measure amount applied to each cone. Feedback system adjusts flow automatically. After coating, cones pass through second cooling stage to solidify layer. Now comes interesting part, decorative rim. You notice the top of the cone has characteristic wavy edge. It's not just aesthetic, it serves practical function. Reinforced rim is stronger and less prone to breaking when employee places ice cream. Rim is created during initial molding but goes through finishing process. Specialized machine presses and shapes rim, guaranteeing uniformity. This also removes any irregular excess that may have formed. Quality control at this point is intense. Regular sampling removes cones from line for destructive testing. They test pressure resistance, measuring how much force is needed to break cone. They test moisture absorption, placing cone in contact with liquid and measuring how long it takes to soften. They test flavor, with tasting panels evaluating cones regularly to guarantee consistency. Any deviation from established standards results in process adjustments. This quality obsession is what allows McDonald's to maintain absolute consistency. The cone you eat in London is identical to one in New York or Tokyo. After testing, approved cones go to packaging. Here another engineering challenge: how to pack millions of fragile cones without breaking them. Cones are extremely delicate. Minimal pressure causes cracks, so packaging needs to be protective but also efficient in cost and space. Chapter 5. The solution is sleeve packaging. Cones are carefully stacked, nested one inside another. This saves space massively. A tower of 10 cones occupies little more space than single cone. Robotic arms pick cones and stack them in perfect sequence. Speed is impressive, hundreds of cones per minute. Cone towers are then inserted into plastic sleeve. Sleeve protects from moisture, dust, and physical damage. It's heat sealed, creating airtight package. Packaging is crucial because cones are hygroscopic, absorbing moisture from air. If exposed to humidity, they lose crispness quickly. Airtight sleeve maintains dry environment, preserving texture for months. Sleeves are placed in cardboard boxes. Each box contains specific quantity, optimized for transport and storage. Boxes are palletized and prepared for shipping. Logistics is massive operation. Cones manufactured in few centralized factories need distribution to thousands of restaurants. Requires coordination of transport, temperature-controlled storage, and sophisticated inventory management. Refrigerated trucks transport cones to regional distribution centers. From there, they're sent to individual restaurants as needed. Inventory management is crucial. Restaurants need sufficient cones for demand, but not so many they occupy precious storage space. Predictive systems based on historical sales, seasonality, and even weather forecast calculate ideal quantities. Yes, weather forecast matters. Hot days dramatically increase ice cream sales. System anticipates this and adjusts deliveries. When cones arrive at restaurant, they're stored in dry area, away from heat and moisture sources. Shelves are organized following FIFO, first in, first out. Guarantees older cones are used first, maintaining freshness. Chapter 6. At the restaurant, final process occurs. Employee takes cone from sleeve, visually checks for defects, though factory inspection makes this rare. Cone is placed in ice cream machine. Here, another interesting aspect. Cone and ice cream were designed to work together perfectly. Diameter of cone opening, height, conical shape. Everything was calculated to receive exactly right amount of ice cream. Ice cream machine dispenses precise volume in characteristic circular motion, creating that perfect spiral. Ice cream is formulated to have specific viscosity and temperature, allowing it to form peak without collapsing. Combination of crispy cone, sweet coating, and creamy ice cream is result of integrated food engineering. Each element was optimized not just individually, but as system. But let's return to cone for a moment. There are aspects consumers never notice, but that are crucial. Color, for example. Specific tone of golden brown isn't accident. Results from controlled caramelization of sugar during cooking. Too light indicates undercooking. Too dark indicates burning. Acceptable range is surprisingly narrow. Texture is another critical factor. Cone needs to be crispy enough to hold ice cream, but not so hard it's difficult to bite. Balance is achieved through precise ingredient formulation and cooking control.